All right, everybody. So this video will be a little bit longer than the others, but it's also the video that we'll be talking about in class on Wednesday, Thursday, and the following Monday. Okay, so we're looking at limits at infinity. So the last video we looked at infinite limits. This time we're looking at limits at infinity. Okay, so if we look at it, we've got if f of x, some function, becomes arbitrarily close to some number L, that's a finite number, for all sufficiently large and positive x. Okay, so what that means is if x is blowing up and getting really big and going off towards infinity, our function is going to get closer and closer to some number value. Okay, so we write that the limit as x approaches infinity of f of x is equal to L, whatever that number is. Okay, in this case, our line y equals L, that value, is going to be our horizontal asymptote. Okay, we can also define the limit as x approaches negative infinity, and there should only be one equal sign in here. Okay, but we can define the limit as x approaches negative infinity of our function f of x to equal m, just some value. Okay, and so we get the horizontal asymptote is the line y equals m. Okay, and a function can cross its horizontal asymptote. Okay, it can't cross a vertical, but it can cross a horizontal. Okay, and a function can have 1, 0, or 2 horizontal asymptotes for the ones we'll be looking at. Okay, so if we do an example, we've got our function here. We want to look at what happens as we take x to negative infinity, and what happens as we take x towards positive infinity. Okay, so if x is getting large and going towards negative infinity, okay, our denominator is going to get really, really big because even though they're negative numbers, it'll be squared. So our denominator is just going to get really, really big, and our numerator is going to stay 1. So it'll go closer and closer and closer to 0. Okay, because as x goes towards negative infinity, the values will get smaller, and well, these values here for x will get, for x squared, it'll get larger and larger. So that means our 1 over those values will just get smaller and smaller fractions. Okay, similarly, if we take, as x goes to positive infinity, our denominator is just going to get really big, really, really big, and so then that fraction will get smaller and smaller and smaller until it approaches 0. So we'll have a horizontal asymptote at y equals 0. Okay, and they don't have to both equal 0 for us to have a horizontal asymptote. As long as one of them equals the value, then that's a horizontal asymptote. So they could equal 2 different values, and we'd have 2 different horizontal asymptotes. We'll see some example of those in a little bit. Okay, so if we look at this function here, we do the limit as x approaches positive or negative infinity. So if I write it like this, that means it's going to be the same for positive and negative infinity. Okay, because I know what the answer is going to turn out to be, I can write it like that. So if we plug in our function, 5 plus sine of x over root x. Okay, as our values get larger and larger, or smaller and smaller, this is just sine of x over root x is just going to equal 0. So our limit of this is going to be 5. So we'll just have a horizontal asymptote at y equals 5. Okay, and that's the same. So if x approaches positive infinity of our function, it's going to equal 5. And as x approaches negative infinity, it'll also equal 5. Okay, so we can combine them and write them that way when that's the case. Okay, we can also look at the limit as x approaches positive or negative infinity for 3x squared minus 9x to the 7 equals 0. All right, so if we're looking, so 3x to the 12th is just going to get really big really quickly. And our number that we're subtracting off is going to get big, but not quite as big. Okay, so we get positive infinity. If for some reason this number was going to be bigger or getting bigger faster than our front number, then it would be negative infinity. Okay, so if we're looking at infinite limits at infinity. So if we're let's combine what we talked about at the beginning of this week, infinite limits, with what we've talked about in this video already, limits at infinity. We get infinite limits at infinity. Okay, that's when a function, as x approaches positive or negative infinity, the function itself goes off towards positive or negative infinity. Okay, so we've got 4 different possibilities that could happen or look like. Okay, some examples of these are even functions. So even functions generally look like this. Okay, and then as x gets large, we're going off towards positive infinity. And as x gets small, we're also going off towards positive infinity. Okay, we've got odd functions. Okay, so as x approaches positive infinity, our limit's going to approach positive infinity. And as x approaches negative infinity, our limit's going to approach negative infinity. Okay, and we've got 2 other likely cases. We've got 1 over x to the n where n is even. Okay, they look like this. Okay, so as x approaches well, this one's not really an example of that one, but we've got as x approaches 0, then our function goes towards infinity, and as it approaches 0 from the left, we also go off towards infinity. But you can see the difference there. Okay, so here we are approaching a number for it to blow up. Okay, and then we've got y over x to the n if n is odd, and if this is the case, then we still don't have actually that example, but we've got something similar. So if we approach 0 from the right, we go off towards positive infinity. If we approach 0 from the left, we go off towards negative infinity. And as x approaches positive infinity, our function gets closer and closer to 0. And then same with approaching negative infinity. Okay, so you can see the difference between these functions up here and these functions down here, where we have infinite limits at infinity. And down here where we just either have an infinite limit or a limit at infinity. Okay. Then we've got a theorem that just runs through a couple different cases. So if we've got limits at infinity of powers and polynomials, okay, so let n just be some positive integer. P is this polynomial. Okay. So the limit as x approaches positive or negative infinity of a polynomial, we're just going to look at the first degree or the highest degree. So in this case, our highest degree is x to the n. Okay, it won't always be the first term, it'll just be the largest exponent. Okay, so if n is even, then that'll equal positive infinity. If n is odd, then as x approaches positive infinity, your function will be approaching positive infinity. And as x approaches negative infinity, the function will approach negative infinity. Okay. If we've got, for example, the limit as 1 over x to the n as x approaches positive or negative infinity, okay, that'll equal 0. Anytime you've got a fraction like this and you're approaching positive or negative infinity, that'll equal 0 always. Okay, and if we're looking at a polynomial, okay, we just take the first term, or the term with the highest degree, the highest exponent, and that'll be positive or negative infinity depending on the degree of the polynomial and the sign of the leading coefficient. Okay, so you treat the degree of the polynomial, that brings you to one of these two cases, and then your coefficient, this a to the n, will either be positive or negative. Okay, so you have to look at those things combined. Okay, something to remember, all of our previous limit laws still apply, like the constant multiplier, and this theorem only works for when x approaches positive or negative infinity. Only works for those cases. Okay. All right, so if we're looking at, do a couple of examples. All right, so if we're looking at our function here, it's the same function from earlier, we're just gonna do it a little differently now that we have this theorem that we can use. So we've got the limit as x approaches positive or negative infinity of our function. Okay, we take highest degree, so largest exponent, and we take that term, so this is the same as the limit as x approaches positive or negative infinity of 3x to the 12th. Okay, and because this is even, right, and this approaches, then approaching both positive and negative infinity, this will be positive infinity. Okay, if 3 had been negative 3, then this would have been negative infinity. But all right, so then we're looking at our function here. Let's look at it. So this one we'll have to do separate. So we'll do the limit as x approaches positive infinity. We've got 2 over x to the 8th plus 4x to the 3rd. So we take the largest exponent's term, so that'll be 4x to the 3rd. I know that 8 is larger than 3, but the 8 is in the denominator. So because that's a fraction, it's smaller. Okay, you can look at, if you're looking at them here, because the 8's negative, then it's smaller. That's another way to look at it. Okay, but so this is equal to the limit as x approaches infinity of 4x to the 3rd. Because that's odd, and we're approaching positive infinity, then our function will approach positive infinity. Okay, and then we can do the limit as x approaches negative infinity of our function. Again, we take the limit as x approaches negative infinity of 4x cubed. Okay, and because this is odd and we're approaching negative infinity, then our result is negative infinity. All right, when we're finding the limit as x approaches either positive or negative infinity of a rational function, so that's a function where it's a polynomial divided by another polynomial, okay? Well, then before we do that, our first step is always going to be to multiply the function by 1 over x to the n over 1 over x to the n, where n is the highest degree in the denominator, okay? And something to remember, in order to receive full credit for this type of question, you've got to show all the fractions in your intermediate steps. Okay, and I'll explain. So if we do an example, okay, so I've got my denominator here, and I only have one term. So I multiply it by 1 over x squared over 1 over x squared, okay, because if I only have one term, it's automatically the greatest. Okay, So this is equal to the limit as x approaches positive infinity of, we distribute, we get 1 over x squared minus 1 over x over x. Okay, and these are what I mean by the intermediate steps. You've got to show what you multiply it by, and you've got to show the resulting limit before you actually evaluate. Okay, so because these two are fractions, they'll both be 0. So it'll be 0 minus 0 over 1. Or 0 over 0 over some positive number, because this will grow and grow and grow. But either way, it'll be 0. Okay. Actually, wait, nope. This will be 1 because this should be 1. Because when we multiply x squared, 1 over x squared, we get 1. All right, and then if we're looking at the limit, so there's that. And then let's see if we look at this limit. Okay, our highest degree is going to be x, just x, so it'll be 1 over x times, or over 1 over x. So we get the limit as x approaches infinity of 1 over x minus x over 2. Okay, so we get 0 minus some infinite number that's going to blow up over 2. So that's going to end up being negative infinity. Okay, because if we've got 0 and we're subtracting infinity, some really big number from it, that's going to be negative. And whatever that number is, if we've got infinity and we divide that by 2, it's still going to be an infinite number. Okay. All right, so we've also got a theorem here where we've got looking at the end behavior and the asymptotes of rational functions. Okay, so if we've got some function that's a rational function, so p over q, where they're both polynomials, okay, there's a couple cases. If our degree of the numerator is less than the degree of the denominator, okay, so the highest exponent in the numerator is less than the highest exponent in the denominator. Okay, if this is the case, then our limit as x approaches positive or negative infinity is going to be 0, and y equals 0 is our horizontal asymptote. Okay. If our degree of our numerator equals the degree of the denominator, then our limit as x approaches positive or negative infinity is going to equal the coefficients of those two leading terms. Okay, and that'll also be our horizontal asymptote. If the degree of our numerator is greater than the degree of our denominator, okay, then as x approaches positive or negative infinity, our function is going to either approach positive or negative infinity, and we won't have any horizontal asymptotes. Okay, then we do have the possibility of what's called a slant asymptote. Okay, if our degree of the numerator is 1 more than the degree of the denominator. So if our degree of the numerator is 3 and the denominator is 2. Okay, then our limit as x approaches positive or negative infinity is still going to be positive or negative infinity. And f will have no horizontal asymptotes, but it'll have a slant asymptote. Okay, and we'll talk about a slant asymptote in just a moment. And then lastly, our vertical asymptote. If our function is in its reduced form, so if we factored and we've canceled everything that we can, then our vertical asymptotes will occur at the zeros of the denominator. So whatever's left in the denominator, set it equal to 0. That'll be your vertical asymptotes. Okay. All right, so we've got an example here. We can evaluate the limits as x approaches positive and negative infinity, and we'll give our equation of our horizontal asymptote. Okay. So either way, we're going to multiply by 1 over x cubed over 1 over x cubed. Okay, because that's our highest degree in the denominator. So that'll be 2 plus 7 over x cubed over 1 minus 1 over x plus 1 over x cubed, or squared, plus 7 over x cubed. Okay, so we did the limit as x approaches positive infinity first, of 2 plus 7 over x cubed over 1 minus 1 over x plus 1 over x squared plus 7 over x cubed. Okay, and that'll end up being, this will go to 0 because it's a fraction, this will go to 0, this will go to 0, and this will go to 0 because they're all fractions. So we're left with 2 over 1, which is just 2. Okay, likewise, we can do our limit as x approaches negative infinity of 2 plus 7 over x cubed over 1 minus 1 over x plus 1 over x squared plus 7 over x cubed. Okay. Again, these same things will all go to 0, and we get 2 over 1, which is just 2. Okay, so our horizontal asymptote will be y equals 2. Okay. So now let's talk about our slant asymptote, because that's a new one for us. Okay, so our slant asymptote, so if the degree of the numerator is greater than the degree of the denominator, then we have what's called an oblique asymptote. Okay, where if we divide p and q using polynomial long division, we get a plus r over q, where r over q is our remainder. Okay, or r is the remainder, but so if we're looking at when m is only 1 more than n, we call this our slant asymptote. So slant asymptote is a special case of the oblique asymptote. But for this class, you'll only really be concerned with the slant asymptote. Okay, so we'll do an example of how to find that. Okay, so we'll first find the vertical asymptotes and then the slant asymptote. Okay. So if we're looking, so remember the vertical asymptotes occur when y is approaching some c over 0, or when the denominator equals 0. Okay. And we can't cancel anything here because it just won't factor to be able to cancel. So our vertical asymptotes will happen when x squared plus 2x is equal to 0. So when x times x plus 2 is equal to 0. So when x is equal to 0 and x is equal to -2. These will be our vertical asymptotes. Okay. All right. So then we can look at the limits as we approach those points. So anytime you're asked for a vertical asymptote, you're generally going to be asked to support that with limits. And so what that means is you'll take the limit as x approaches the right or the left and show that that limit equals positive or negative infinity. Okay, so we'll do that if we've got limit as x approaches 0 from the left of our function 2x cubed plus x cubed, or sorry, x squared plus x plus 3 over x times x plus 2. So we can plug 0 into the denominator and we get 3. If we plug 0 in for x plus 2, that'll give us 2. Okay, and 0 here, we can't just plug it in because that's what would give us the denominator of x. But if we're looking at 0 from the left, it'll be some negative number. So that'll mean our answer will be negative infinity. Okay, we can do the same for when x approaches 0 from the right. Okay, we'll again still get 3 because we're just plugging in 0, and we'll get 2 over here still. But the difference will be because we're coming from the right, we'll get some positive number, which will give us positive infinity. Okay, so that's supporting that x equals 0 is a vertical asymptote. So now we'll look at the limit as x approaches 2 from the right. Sorry, negative 2 of our function. Okay, so if we plug negative 2 in, we get negative 11 in the numerator. And here it's swapped. So here the issue is with this x plus 2. Because we can't just plug negative 2 in because that'll be 0. But we get a negative 2 from here. And then here, if we're looking at negative 2 from the right, we're looking at all the values that are smaller than negative 2. Okay. And so if I add 2 to any of those, sorry, I'm looking at all the values that are greater than negative 2. So if I add 2 to those, then it'll give me some positive number. So we get positive infinity. And if I look at the limit as x approaches negative 2 from the left, again, follows the same process. We get negative 11 and we get negative 2. But if I'm looking at it from the left, we're looking at all the values that are less than negative 2. So if I add 2 to any of those, I'm just going to get some negative number. So we get negative infinity. Okay, so there we've supported our answer. So supported vertical asymptotes with limits here. So we first found the vertical asymptotes. Then we supported them. All right, and then lastly, we're going to find our slant asymptote. Okay, we know we have a slant asymptote because the highest degree of the numerator is 1 more than the highest exponent in our denominator. Okay, so we do polynomial long division to find our slant asymptote. So it'll be x squared plus 2x divided by 2x cubed plus x squared plus x plus 3. Okay, so x squared plus 2x will go into these first 3 terms 2x times. And that'll be minus, so 2x cubed plus 4x squared, which will give us negative 3x, and then we bring down this x here. Okay. So then our x squared plus 2x will go into this negative 3 times. So we get minus negative 3x squared. That should be an x squared. Negative 3x squared minus okay, which will give us a positive 7x, and then we bring this 3 down. And x squared plus 2x is not going to be able to divide into 7x plus 3 anymore, so we have a remainder. Okay, so our slant asymptote is that whole number version or piece of it. Okay, so we could rewrite this as, so we can rewrite y as 2x minus 3 plus our remainder 7x plus 3 divided by x squared plus 2x. Just like if we were doing long division with numbers and ended up with a remainder. Okay, and then our slant asymptote is this 2x, so it's y equals x minus 3. That's our slant asymptote. Okay, so you take whatever the whole number piece, okay, is one way to think about it. All right, if our denominator has a square root, then we might need to change our work, depending on whether x is approaching positive or negative infinity. Okay, so here we've got a square root of x to the 6th. Okay, if we square root x to the 6th, that gives us x to the 3rd. And so our highest value is going to be 1 over x to the 3rd. So we multiply by that. Okay, and then we do most of it exactly the same, and we just have one little thing that we do instead. So let's do the limit as x approaches positive infinity. So we multiply everything by 1 over x to the 3rd, and we get 7 minus 2 over x to the 3rd over -1 minus 1 over root x squared. So that's the same as just saying 1 over x, okay, divided by 25x to the 6 plus 4. Okay. Oh, that should be a positive. Okay. So remember, 1 over x to the 3rd is the same as 1 over square root of x to the 6th. Okay, so when we need to multiply by a fraction or by a root like that, we have to use that equivalent relation. Okay, and so if we're approaching positive infinity, then that's a positive. Okay, if we're approaching negative infinity, so if we do the limit as x approaches negative infinity, okay, for the most part, this will look exactly the same, except okay, if we're approaching negative infinity, when we do that equivalence relation with the radical, that becomes negative. Okay, but that's the only thing that's different. All right, so we can finish and we get that equals 0 because it's a fraction. And likewise, that equals 0. So we get 7 over -1 plus root 25 plus 4 over x squared. Okay, likewise, we get 7 over -1 minus root 25 plus 4 over x squared. Okay, that goes off to 0 inside the radical. So we get 7 over -1 plus root 25 and 7 over -1 minus root 25. So we get 7 divided by -1, or root 25 is just 5. So we get 7 divided by 4 and -7 divided by 6. Okay. So in this case, we have horizontal asymptotes at y equals 7/4 and equals -7/6. Okay, so we can have 2. All right. So let's say we've got, sometimes you might get asked a question where you're given a list of attributes and they say, hey, graph a function that has all these properties. Okay, so if that's the case, we'll have to go property by property. So the first thing I would look for was any points that you know either exist or don't exist. Okay, so we know that f1 is going to equal 1, so we'll have a point at 1, 1. Okay, and we know that f of 2 won't exist. So look for a limit then. So the limit as x approaches 2 is going to equal 5/4, which is going to be right over, a little over 1, and we know it'll have a hole because that function doesn't exist there. Okay, and then you want to go just line by line. So as x approaches 0, it's going to go towards negative infinity, so it'll be negative infinity for both sides approaching 0. And we know that f of -1 is going to equal -1. Right. And then as x approaches positive and negative infinity, the function's going to approach 1. Okay, so as x approaches negative infinity, the function will approach 1. And as it approaches positive infinity, the function is going to approach 1. Okay, so our function will be shaped somewhat like this. So we can start off here. We know we're going to infinity. We've got this point here. And then we go off towards that way. And then we can do the same thing for this side. Okay, so just take it case by case with the properties and then fill in a graph that fits all of those. Okay. All right, there's 2 more examples on here. I'm going to wait and do those in class. But that way you have them and you can attempt them if you want to before I do them in class.